Hi, Bobcats. In this segment and the next, we're going to take a brief look at a couple of items that chemists borrow from physicists. We talked earlier in this chapter about how all of the science fields are interrelated to one another, and this is a great example of some topics that really belong more in the realm of physics that we use all the time in chemistry. The first of our objectives is to compare and contrast the concepts of weight and mass. And then the second is to use the equation for density, and we're going to do a little bit of manipulation of it. We want to be able to solve it for D or for M or for V. The concepts of mass and weight are very closely connected. Mass is a measurement of how much matter is present. The number that you have for mass will be the same no matter where you are, no matter what planet you're on. Weight, though, is the force of gravity acting on matter. And since it's directly tied to the strength of gravity, it will change as the gravity changes. So if you go from one planet to another, it's different. This is a very important distinction for physics. For chemists, we generally tend to interchange these two terms because we're pretty much always doing our chemistry on Earth. This question is an example of something you might see on the concept of weight versus mass. It's telling us that on the moon, gravity is about 1/6 that of Earth, so things are going to weigh less on the moon. If an astronaut weighs 180 pounds on Earth, how much would he weigh on the moon? Well, 180 pounds is how much he weighs on Earth, and we have 1/6 the gravity. So we're going to multiply by 1/6. 6 goes into 18 3 times, and there's still a 0, so 30 pounds. 30 pounds is how much that astronaut would weigh on the moon. This question is very similar to the previous one, but this one's getting at the concept of mass. The astronaut has a mass of 72 kilograms on the Earth, and again, the gravity is 1/6 Earth's gravity when you're up on the moon. So what would his mass be on the moon? Well, don't fall for this. Don't do any calculations. Mass is the same no matter what the gravity is. So his mass on the moon would be 72 kilograms. Density is another common physics thing that pops up a lot in chemistry. It's illustrated with this glass showing what's called a density column. Colored liquids that have different densities remain layered in this glass instead of mixing because the most dense liquid will stay at the bottom, the least dense liquid is floating on top. When we look at density from a mathematical side, we have this equation D equals M over V. D stands for density. I guess I should probably connect that. M stands for mass, and V stands for volume. So we need this equation allows us to relate the mass and the volume of a sample to its density. When we're doing calculations on density, sometimes we're asked to find density. So they'll give us mass and they'll give us volume and they'll say, hey, what's the density? In that case, you just plug it straight into this equation, you run it through your calculator, and you have your answer. But that might not be all that they do. Maybe they give you mass and density and want you to find volume, or maybe they give you density and volume and want you to find mass. We should be able to use algebra to rearrange this equation to solve for any of the variables. Now, the one that gets a little tricky is solving for a variable that's in the denominator, which in this case is V. So the technique that I'm going to use to rearrange this equation is to simply get rid of the denominator. If we're not looking at a denominator, it's amazing how much more accurate our calculations tend to be. So to get rid of that denominator, since we're dividing by v, I need to do the opposite. I need to multiply by v. And if I multiply one side by v, I've got to multiply the other side by v as well. So if I start with density equals mass over volume, and I multiply the side by v to cancel it out, I've got to multiply the other side by v as well. And so I end up with volume times density is equal to mass because the v's cancel out. So that's one other form of this equation. It is now solved for mass. We just take the volume and multiply it by the density. But if I'm going to rearrange this equation to solve for volume, that's the equation where I want to start, actually, because I have removed, let's try again. I have removed the denominator, so I will have volume times density is equal to mass as my starting point. Right now, volume is multiplied by density, so to get volume by itself, I need to divide by density. And if I do it to one side of the equation, I've got to do it to the other side as well. The density terms on the left cancel out, and I have volume is equal to mass divided by density. So now we have the three equivalent forms of this equation. We have that density is equal to mass over volume, volume times density is equal to mass, and volume is equal to mass over density. For this example, we're asked to find the volume of 50 grams of gold, given that the density of gold is 19.3 grams per cubic centimeter. Okay, so if we have 50 grams, what will that volume be? Well, on the previous slide, we saw that the equation for density is mass over volume. And then we really need to solve this equation for volume. Well, since it's in the denominator, we need to move it out of the denominator first. So we'll have density times volume is equal to mass. That's what we get when we multiply both sides by v. And now to get v by itself, we'll divide by d, and we end up with volume is equal to mass divided by density. So now that we have this form of the equation, let's just plug our numbers in. Volume is equal to 50.0 grams divided by 19.3 grams per cubic centimeter. And if you crank that through your calculator, 50 divided by 19.3, let's see, my calculator is saying 2.59. The units of grams cancel out, and we have 1 over cubic centimeters in the denominator. So if we invert and multiply, that's just going to give us plain old cubic centimeters. 2.59 cubic centimeters for the volume of 50 grams of gold. To wrap up this section, let's revisit our objectives. The first was to compare and contrast mass and weight. Mass tells you how much matter you have, so it's the same no matter where you are, but weight will be different on different planets because it's how that mass interacts with gravity. So if gravity changes, you have a different weight. And then we also looked at the density equation in its three forms: D equals m over v, m equals density times volume, and volume is equal to mass divided by density. And I got to preach a little bit about how solving for variables in the denominator can be tricky. So make sure that you clear out the denominator first.